As Richard Feynman famously said, things on a small scale behave nothing like things on a large scale. And I'm interested in why that is and hope to be enlightened in the course of this discussion. I'm holding 4 figures in my head. Well, actually, I've written them down, but in due course they may insert themselves into my head. A nanometer is 1/1000th of a meter. A human hair is 100,000 nanometers. A red blood cell is 7,000 nanometers. And a nanomaterial is less than 100 nanometers. Now, nanotechnology is seen as the next great frontier of science and medicine. But I note that there is a great deal of uncertainty around the world about the implications of it. A Royal Commission on Environmental Pollution in the UK just a couple of years ago said there is profound ignorance and uncertainty about the behaviour of some types of nanomaterial in the environment and the risks they pose for human health, and virtually no data on long-term effects. Here in New Zealand, the Sustainability Council says our exposure to nanomaterials, especially in cosmetics and sunscreens, has taken place well below any regulatory oversight. So why are some so excited about nanotechnology, and why are others so worried? And how can we harness the benefits while minimizing any dangers, is the question that we're here to kick around. Here to enlighten us, Shaun Hendy, a nanotechnology expert, Deputy Director of the MacDiarmid Institute for Advanced Materials and Nanotechnology in Wellington. Sally Gaw, lecturer in environmental chemistry at the Department of Chemistry at the University of Canterbury here. Hans van der Voort, chief executive and founder of Eyes on Science, which he tells me is the only nanotech company in New Zealand actually exporting anything. Is that right?
I think so.
Yes, all right. Peter Dawson, principal scientist at the Environmental Risk Management Authority, or IRMA. Jamie Ataria is with Landcare Research in the Sustainability and Society Group, and he has a PhD in ecotoxicology. He's involved in researching more reviews of new technologies. And Georgia Miller, who's coordinator of Friends of the Earth Nanotechnology Project, co-author of a report about nanotechnology in food and agriculture. Please welcome the panel, ladies and gentlemen. You'll have a chance to ask questions a little later, but first of all, I want to ask each of the panel to talk a little, 2 or 3 minutes, about what nanotechnology means to them, beginning with Shaun Hendy.
Oh, thanks, Kim. Yeah, so well, Kim's given a very nice introduction to what a nanometer is, and perhaps I'll take over.
Did I get it right?
Yes, you did. That's great. So it saves me the trouble of getting my billionths muddled with my millionths. So I just want to talk about what nanotechnology is. So nanotechnology is really about manipulating materials and technologies on the scale of the nanometer. So, you know, the nanometer scale, to give you another perspective, one nanometer is about 10 times, you know, if you line up a bunch of atoms and across a distance of a nanometer, you could line up about 10 atoms across that distance. So it's about manipulating matter on the atomic scale, and really, you know, from a technological point of view, that's about as good as we can get in some ways. So why are we talking about it now? Well, you know, why weren't we talking about it 50 years ago, or why are we just not worrying about it now? And that's really because we've started to get very good at manipulating material down at that scale. And a lot of you will have things that have materials that have been manipulated on that scale. For example, if you bought a laptop or a computer or a cell phone recently, there'll be bits and pieces of that technology that really we can look at as nanotechnology. There's materials have been manipulated on that scale. So why are we doing it? Well, actually, there's lots of different reasons why you might want to do it. to make a faster laptop or a cheaper cell phone, for example. But I actually asked my students, you know, why I lead a group of about a dozen research students in their 20s and 30s. Why have they come to work with me? They come from all over the world. You know, there's people from India, the United States, and even someone from Wanganui. And you know, they've got all sorts of backgrounds: physics, chemistry, law. One of them even used to be a fighter pilot in the US Air Force, and they've come to work in nanotechnology in New Zealand. Why are they doing it? Well, it's because they're worried about the future. You know, if I ask them, this is what actually comes out, they don't necessarily tell me straight up that this is what they're concerned about, but they're thinking about what the world's going to be like in 2050, and they're aware of the fact there might be another 3 billion people on the planet, and probably those people are going to be quite wealthy compared to people today. And once you become rich, you start using more energy. And in fact, if you know, back of an envelope calculation, we might be using 3 times the amount of energy in 2050 that we are today. And the scary thing is we're actually not going to run out because there's quite a lot, you know, there's plenty of energy available in things like coal. The problem is we don't want to be burning coal at that rate. So we've got to look for new ways of generating energy. And one of the ways that a lot of scientists think, you know, we're going to have to go is to use solar cells and photovoltaics. And actually that's kind of an old technology. It's not something that is very recent, is just recent. Solar cells were first demonstrated in the 1950s in Bell Labs. So they've been with us a while. Why don't we all have them? Well, it's actually because they're quite expensive, not just the solar cell itself, but the device and the technology that we have to embed the cell in. And really, a lot of the young people today are working towards, or the ambition is to work towards a world where we can afford solar cell technology. So we can move to an economy that's green and support all these extra people with a standard of living that perhaps New Zealanders enjoy today.
Just one question. Why would nanotechnology make it cheaper?
Yeah, no, that's a good question. It might not. For example, you know, I mean, so we've had silicon solar cells for 50 years. People have been working on, and they are getting cheaper because of mass production techniques. But nanomaterials, for example, would potentially give us the possibility of capturing a broader range of the solar spectrum. So in fact, may not necessarily make it cheaper, but you might actually be able to generate more electricity using a nano-based solar cell. And that cell will pay for itself faster. So you'll get a return from your investment in a shorter amount of time.
Is that a formula you've got in front of you there?
That's just my notes.
I'm hesitant to ask you why nanotechnology would enable us to capture more energy, but I want to. Can you explain simply?
In a simple way, it's about improving the properties of materials. So by being able to manipulate atoms down at the scale, you know, we can create materials that haven't existed before, that have new properties, that perhaps allow us to capture different parts of the solar spectrum, or that are in fact easier to manufacture than silicon, for example.
Thank you. Sally Gaw.
Thank you, and thank you to everyone for joining us tonight. I had to think long and hard about this. So where I sit with nanomaterials or nanotechnology is it's quite an exciting technology, and it's a collection of technologies that has a lot of potential. But like all of our chemistries, there are pros, cons, and challenges. And we're going to have to work out what are going to be acceptable uses of nanotechnology, what are valuable uses, like the ones Shaun has been discussing, and what are the frivolous ones. So by frivolous, I mean, do we need it in some of our cosmetics? Remember that when we change these properties, and we are deliberately changing these materials for specific properties, we may also change their toxicity. We may also change what happens to them when they're released into the environment. So an idea of a frivolous technology might be silver nanoparticles. There's a beneficial use of them where they might be used in wound dressings, where they're antimicrobial, and that might help people who've got severe burns. Versus the other end of the scale, where you can put them in your socks and your underwear. And we're not all astronauts. And then you can also add them to babies' nappies. So what are some of the challenges that I see? It's going to be around doing the risk assessments, about being able to decide when there is a plethora of nanotechnologies, which ones are going to be safe, for want of a better word, and which ones are we going to say, hey, we're not going to use that. Now, we've already been through this process. Think of some of the pesticides. Some of the audience will be aware there were things that they could use in their home garden and now they can't. And that has been risk assessments being done, people learning more about the chemistries and deciding which ones are acceptable and which ones are not. So these challenges are not all unique to nanotechnology, but some of them will be. The things around, if you change the properties, does it matter? And it does. So a traditional risk assessment would just say we've got chemical X. Now we have a wide variety of chemical X, which is also this different shape. And shape and size and composition are going to start mattering for our toxicity. There is a lot of literature that people can draw on to start doing this. And I would like to see some people start doing this at the planning stage. We want to make this. Does it look like asbestos? Does it not? Does it already contain toxic metals that we already know we have a problem with? So if we know that arsenic, cadmium and lead are already toxic to humans, why would we put them in a different form? Particularly if they're going to be where the population's going to come in contact with them. The other challenge is around the safety. These are materials with unknown properties when they start developing in the labs. How do we protect the people who are working with them? And what do they need to know? And what do we need to know, particularly if we're supervising them? Currently, also, there are limited measurement options for finding these things in the environment or measuring them in a lab. I believe my colleague to the left is going to talk a little bit more about that. And so I'm excited to see what changes in analytical chemistry, which is one of my fields, as we work through what do we need to be able to do to find these things. Because we don't actually know where they are or where they go in the environment very easily. So a way forward, I think, is to use greater use of existing literature. What do we already know? There's a lot of information around particles and the effects that they have when people breathe them in. That's one of the reasons that Christchurch did have, which has just been rescinded, the improving air quality. That was around getting particles out of the air. So can we draw on that literature? I'd like to see more people think about toxicity and about what they're making at the design stage and right through the life cycle. If you're designing for a product, right from when you make it, the people who make it need to be protected, right to whoever has to look after it when you've finished with that product. And we are going to have to decide which applications are acceptable. The same with all the other technologies that we have developed. And I thank you for listening.
You mentioned arsenic, cadmium and lead. Are you suggesting that those are in nanoparticles being used?
They can be, yes.
What for?
Cadmium is definitely in quantum dots, which are used in imaging.
Okay. Arsenic?
Arsenic I can't remember, but I do know that some are arsenic-based, or can be.
You mean it's possible to make nanoparticles of arsenic, but you don't know whether people are actually using them?
No, I know they are, but most of those at the moment are in research laboratories rather than in commercial products or being used.
All right. Thank you.